So, we're stranded on a desert island with all of the components necessary to assemble an electrochemical cell to power our radio or something. Lucky us. We have available to us zinc metal, zinc nitrate solution, copper metal, and copper 2 nitrate solution, as well as all the glassware and salt bridges and all that fun stuff. Lucky us. Let's see how we can arrange this cell so that we can get out voltaic, so something that's spontaneous that will produce electricity for us. So that means we want our cell potential to be positive. That means a spontaneous reaction. That's what we're looking for. And so remember that our cell potential overall is going to be our reduction minus our oxidation process. Or if we wanted to think that's the cathode and the anode. So we can set this up. Really, when we're given two reactions to combine together in such a way that will make a cell, even if we don't remember anything about what's better oxidizing agent, what's better reducing agent, throw the numbers in and see what happens. Let's try it where we keep the zinc one as our cathode and our copper at the anode. Let's see what we get there. If we do that, if we do the zinc at the cathode and copper at the anode, we'll get the following. Our cell potential will equal negative 0.760 minus positive 0.337. These would be volts, bringing it at negative 1. I can do this. 0.97? Question mark? No, that can't be right. Okay, bust out the calculator. Let's do this properly. 760 and 337. Oops, I didn't put the decimal properly. Plus 0.337. Oh, wow, I got it right. What do you know? Okay, so that's our cell potential here. Very negative, not what we want. So, if we switch those two, we should get the positive of this number, but let's double check. Let's do it. If we do the opposite way, if we do the Cu at the cathode, can't change both of them, right? I can only change one. And then the zinc at the anode, we get the following. We have our cell will be equal to 0.337, that's a positive value, minus negative 0.760, which will equal positive 1.097 volts. So this is what we're looking for. We're looking for the copper to be the cathode, which means anox red cat, copper should be reduced, and therefore zinc should be oxidized. And if we take our reactions, remember these reactions are always written as reductions. So if copper is the one that needs to be reduced, leave that equation alone. If the zinc needs to be oxidized, that means that we need to flip that equation around. We'll end up having copper 2 plus, the number of electrons are the same, I'm just not going to include them, plus zinc turns into zinc 2 plus Cu. And so we should see copper being reduced. Indeed, its oxidation number goes from +2 to 0. And zinc should be oxidized. So zinc is going from 0 to +2. That's oxidation. We're all set. This is the reaction that's going to take place in our voltaic cell. All right, so we've seen how to arrange them. We want to arrange the copper at the cathode, the zinc at the anode, and then we're going to see the following reaction take place once we hook everything up. So there we have it, and now we have produced 1 volt of electricity at these conditions. which we'll learn to mess with next week. I don't want to throw that at you quite yet. Right now at our standard conditions, this is what we're going to get. So that's how you can use a voltaic cell. In summary for what we did, we looked at our equation for determining overall cell potential. We plugged in numbers randomly. We decided to try one set of conditions out. It turned out very badly. We got a very electrolytic cell out. Not what we want, though. We want a positive potential. And if we tried the other way, we got a nice positive potential overall. And so we saw which reaction needed to be the reduction, which one needs to be the oxidation. And then we were able to add those two together after flipping our oxidation reaction around. And so that's how our cell would be constructed.